Can you hear me now?
Yes, we can.
Okay, perfect.
And we can see your slides.
Very nice. So today I'd like to introduce you to our work that we've done around SOFAStorage. So with this fairly bulky title of creating a vendor-agnostic framework to enable seamless storage offload using SmartNICs. So let's get started by setting some terminology that we are using in this presentation. Starting with the mindset that we're looking at a cloud data center where there are several compute nodes that you can see on the right-hand side, and there are a few less control nodes within that data center running the cloud. The compute nodes are running the customer workloads inside virtual machines. You can see them on the right, red boxes on the right. And they are separated and controlled by a hypervisor that is underneath. Additionally, these compute nodes may be equipped with additional hardware, such as GPU accelerator cards or graph core accelerator cards. FPGA cards are common these days. They're equipped with BMC controllers to start and stop or power cycle these compute nodes. And as well now they are equipped with SmartNICs to connect them to the network infrastructure of the data center. The control nodes themselves run cloud infrastructure management applications and code, such as the node manager that keeps an inventory of all the compute nodes, and let's say a scheduler that is responsible for scheduling the various customer compute requests onto these compute nodes inside the data center. The trusted control plane would be lying, so the control nodes themselves are considered a trusted environment, as well as the hardware that is sitting on the compute nodes, whereas a workload domain is considered everything where a customer workload is running inside. So a CPU and memory on the compute nodes is considered workload domain. So now where comes the motivation on what we're doing? So we're trying to for the schedulers and node managers to communicate with the compute nodes, there is always a little piece of software still running inside the workload domain and on the compute nodes themselves. They are needed to interact with the hypervisor to start and stop virtual machines. They are needed to set up the customer's virtual network functions, including some packet filtering or implications on the proof, and interact with anything that is running on these compute nodes. So the idea now is to, sorry, Ian, you want to annotate something? I cannot control my presentation anymore. Oh, there we go. The motivation is now to move these agents that are running on the compute nodes themselves and move them to the SmartNIC environment, which is then considered a trusted environment where the agents are running. This frees the CPU for running additional customer workloads inside the compute node itself, but it also offers additional security and isolation aspects that if, say, the compute node is compromised by someone breaking out of the VM, they can still not mess around on the data center infrastructure network, as the agents and the communication would still only happen via the SmartNIC. Additionally, this harmonizes the management of how virtual machines and also bare metal offerings are deployed to the cloud environment. And SmartNICs today certainly offer these capabilities, as they are mostly equipped with strong, nowadays, ARM cores that can run any arbitrary applications. Of course, they're all equipped with powerful network interfaces and accelerators that are running there. And additionally, these days now they are equipped with accelerator functions for storage offload. But all of these accelerators and possibilities to offload functions are done via the individual vendor-specific APIs or software frameworks. So it is cumbersome for a cloud company to, say, deploy multiple different SmartNIC vendors to their infrastructure because they need to keep all of their software up to date with different vendor frameworks that they are offering. So there's no common APIs that we can use today to use the accelerator functions in different SmartNICs that we have today. I know there's some functionality around P4 programming languages that you can specify certain data planes for network interfaces, but we are not aware of anything that is offering such a capability for storage offload, for example, that we're looking at today. So with that comes a mission statement that we would say we need to define a single API that allows us to leverage SmartNICs from different vendors to improve the security and performance in a cloud environment. So that basically puts our work into a single sentence and what we're trying to achieve here. We're not the only ones. I think has been a release for the infrastructure programming development kit, which has now also ended in the open programmable infrastructure project. So there is this type of work has been acknowledged, and there are communities being formed to trying to standardize interactions with SmartNICs from the outside. Our take on this is called SOFA. It had an acronym that had various meanings at some point. The latest I know of is Secure Offload Framework for the Cloud. So if we're looking at this slide right here, we again see on the right side, the blue box is a control node, which would be controlling the compute nodes and the customer workloads in the cloud. On the bottom right, we have a storage provider. In this case, we used a NVMe over Fabric storage provider. And then we have the large box, which is a compute node a bit zoomed in. The purple boxes are SOFA components. So we have a front end that is running on the SmartNIC devices that is accessible via the network. These connections are vendor agnostic APIs and are implemented using gRPC function calls. So the control node can essentially call SOFA functions via the front end part. The front end is responsible for authenticating the requests and also allowing the individual components of SOFA, namely the VM agent, network, and storage, to communicate amongst each other. All of these individual vendor agnostic APIs are again implemented in gRPC format so that the front end can easily forward requests to these agents. The VM agent is responsible for starting and stopping virtual machines that belong to customers. So it talks now with a vendor-specific API to the hypervisor that is running on the host to start and stop these virtual machines and configure them appropriately. The network component is implementing the virtual networking function, say, for the customer for the connectivity of the virtual machines. So it will mainly configure the NIC hardware or any required setups that need to be done on the SmartNIC to implement these network functions. And lastly, we have the storage component, which can also now configure, if offered by the SmartNIC, configure the SmartNIC's hardware accelerators, such as NVMe over fabric acceleration is often an accelerator block that is in the ASIC, or set up any other software-based storage provider that can be set up on the ARM device itself by setting up SPDK, for example. So the storage component will take care of sending or setting up the SmartNIC in such a way that it can communicate to the storage provider and provide the volume to the virtual machine on the host. Again, these functions are then happening via vendor-specific APIs. Our approach for the API on the storage component was starting from a high level. So instead of looking at the individual API calls necessary on the SmartNIC, we came from the control node side of things. So we tried to look at, or we looked at the Kubernetes container storage interface and what is necessary for a volume to be exposed or to a container in their language, but it can be a VM in any case. So we have this type of volume lifecycle that we have. So starting on the green box on the left, the control node would receive a call that it would create a volume. So we end up in the created state of the volume. And then the controller again would receive so the control node would receive a call that now it should attach a volume to a running VM, or even before the VM is running, it should attach a boot volume. So it can attach the volume to a specific node, compute node. And so only the two lower function calls would be calls that the control node would send to the SmartNIC for publishing the volume to a configured virtual machine instance on the compute node. And then we consider the volume to be published and usable by the virtual machine. If we take a bit of a deeper look at how we defined the request for such a DPU publish volume call, it is more of an encapsulation of, say, what type of attributes are necessary for a specific vendor to set up the volume on the host. So there are a few parameters that we fixed, or we set up as fixed values, or you need to define a volume ID so you can clearly identify the volume. And but then there's a map, which is a key value store essentially, or a key value array that you can have a volume context and put any type of parameters inside that you need to set up the volume appropriately. So this allows us to essentially wrap around parameters varying from NVMe over fabric offload, or NFS offloads, or iSCSI protocols to vary their parameters with this starting API that we set up here. Again, there's a few fixed things like controller ID, the network's target path, and also the secrets are a key value table or map to send any type of secrets that are necessary to set up, say, in data at rest encryption, or also in-flight encryption for the communication to the storage provider backend. So you see, it's more of a API that we defined that encapsulates things than prescribes things how or what needs to be sent over. So it's a starting point API, I would call it. We did our proof of concept implementation with a NVIDIA Bluefield 1 and 2 SmartNIC. So now we see the SOFAStorage part can run as a standalone component. of SOFA so that we can only use SOFA if we want to. It has been implemented using Python and communicates or makes use of a plugin type. So the SmartNICs vendors would only need to write a small piece of code that defines the plugin that then translates the generic or vendor agnostic API of SOFA into specific API calls that are necessary to set up the storage volumes on the SmartNICs and host. In case of Bluefield, the software environment is, I think, Docker, and for storage, the storage framework is called Snap. So we're now communicating with a Mellanox Snap daemon that is running on the Bluefield cards, and we can set up NVMe over Fabric targets, I think is the correct name, to be exposed on the host to get there. So once our control node now receives the create volume command, it will create a volume of a specific size on the storage provider. And then it will call the DPU publish volume function on the Bluefield with the according parameters and also with the according secrets to implement the data at rest encryption and data in flight encryption. So we now have the volume on the storage provider being encrypted, or is an encrypted volume. It is going through the NICs hardware, where the key or the secret is maintained to decrypt the volume data, and so the VM has direct access to the unencrypted device now or volume that has been exposed to it. So here's a nice example where we can see that the secret data is residing still in an environment that sits outside of the compute node, so that there is no sensitive data being exposed on the compute node itself. So if there's a bad guy inside of VM breaking out, there's no key on the compute node itself that would be able to access the key. That includes already the SOFAStorage API part. We then also looked at, okay, how can we take this one step further and make a nice, say, demo, or you make it a use case in a real world scenario. And since we came from the container storage interface in Kubernetes, we implemented a container storage interface proxy that allows us to deploy the SOFA framework to the SmartNICs and allows Kubernetes to make use of the SmartNICs functions via SOFA directly without changing any of the CSI vendor plugins that are necessary. So if we take a look at how Kubernetes is set up, it very much looks like a small cloud environment. So you have a set of control nodes, big blue box on the left, and a set of worker nodes, which is the blue box on the right side, where the kubelet is running in, which is a small, say, helper agent that sets up the containers that are running there, and Kubernetes makes use of the kubelet to control the containers or pods running on the control and worker nodes. And since we're talking about storage, we also have the storage system on the bottom side. So we have a small cloud setup essentially with Kubernetes. Now, the container storage interface is a standardized interface for the kubelet to talk to a plugin that can be written by data storage system providers. So they can implement these plugins to set up or then communicate with the storage system to say create, delete volumes on the storage system, and also expose them to pods running on the worker nodes or also on the control nodes. So like publish and unpublish these volumes. So it's a standardized way to set these things up. And so for example, IBM would write a CSI plugin to communicate with their storage systems and set up these volumes as requested by Kubernetes via the kubelet agents. So what we now implemented is this CSI Proxy, which is now the purple boxes on the top. So now you can see we let the kubelet communicate with the CSI SOFA plugin or proxy plugin before it actually communicates with the CSI vendor plugins that are talking to the actual storage system. So on the left side, we have one plugin part that is communicating with the controller vendor plugin, which is talking to the storage system for setting up the volumes. And then there's always the CSI node plugin, which is running on all nodes across the Kubernetes cluster. And also here we have the SOFA plugin being the proxy in between to catch any calls that we might want to redirect to a SmartNIC. Now we can have a worker node either with or without a SmartNIC. So if it's without the SmartNIC, with the SOFA plugin, CSI SOFA plugin would simply advance the calls to the CSI node vendor plugin for it to set up the volume as in any traditional way. But in case the CSI SOFA plugin would detect the SmartNIC on the system, it would then make use of the SOFA API that we've seen before to talk to the SmartNIC and the CSI node vendor plugin running on the SmartNIC now to actually expose the volume finally on the POPT. So the yellow box on the worker node itself is exposed via SOFA or Mellanox Snap in this case. And the CSI node vendor plugin would be used to set up the volume on the SmartNIC. Now, this may seem a bit strange first, but this allows a completely transparent way for the vendor plugins. They don't need to be altered or changed in any way for them to be usable via these SmartNICs. So this comes with maybe a performance penalty depending on what type of storage system is being used, but it certainly offers a security enhancement that all of the sensitive data is being stored on the SmartNIC itself. All of this is happening in our open source space and IBM repository, so you're free to look around there and try to set up if you have access to any SmartNIC hardware. You can try to set it up. It's all there with the according example to implement the lifecycle that I've shown before. Also, the SOFA CSI proxy plugin is there for you to set up a small Kubernetes cluster and see if things are working with your environment. And we're more than happy to receive contributions or comments to our API definition that we've started with. As I said, it's more of a vehicle to wrap around an API and send it to the SmartNIC and implement things. But I'm sure that over time we can develop a more concrete API that defines clear API function calls that are necessary for the individual vendors to implement the functions that are necessary for cloud vendors to operate SmartNICs in their environments. And with that, I'm done. Thank you.
Cool. Thank you, Raphael. Let's see. Well, I have one question queued up, but I'd like to encourage others while we're addressing this one. We had one question that was, when you're stacking the nodes into a GraphCore cluster, it seems like the storage is only from the control node. Are you planning on extending out the memory capabilities for users?
Oh, wow. Can you repeat that question again?
Sure. I apologize. So when you're stacking the nodes into a GraphCore cluster, it seems like the storage is only from the control node. And the question is, are you planning on extending out the memory capabilities for users?
I need to take that offline. I'm not sure if I understand that question correctly.
Sure. Okay. Are there any other questions? I don't have anything else queued up at the moment, but any other questions for Raphael? Okay. Thank you, Raphael. I appreciate the time. Good presentation.
Thank you.